Yes, I think we're close to being on time. And to allow the most time, let's just get started. And let me introduce Chris Urmson, our speaker today. He is the co-founder and CEO of Aurora, and that is the company that has consolidated most of the other self-driving vehicle startups into one entity. So it's the company is delivering the benefits of self-driving technology, and it's doing it very quickly and very broadly. Chris has been instrumental in instigating and advancing self-driving vehicles for the last 15 years, so he really started very early. And before founding Aurora, he helped start Google's self-driving car program and served as its CTO. Previously, Chris was a faculty member at the Robotics Institute at Carnegie Mellon University, where he worked with house-sized trucks, which I assume those are the ones that are used in mining.
Yep.
Is that right, Chris?
Yeah, no, these gigantic, like they're just incredible. I'm excited about the trucks we work with today. And these things are literally the size of houses. It's amazing to work with.
And he drove robots in the desert, and he was the technical director of the DARPA Urban and Grand Challenge teams. He earned his PhD in robotics from Carnegie Mellon and his bachelor's degree in computer engineering from the University of Manitoba. So Chris, please get started.
Great. Well, thanks for having me. I really appreciate the opportunity to talk to everyone today about what we've been up to at Aurora, and kind of give a little bit of an overview of the self-driving space and some cool stuff about lidar. First, I'm going to apologize up front, as I said to our wonderful hosts. This is the first time I've given a lecture in this format, and it's a little bizarre doing it without being able to see you all. So my apologies up front, but we'll see how it goes. So I'm going to jump in and just talk a little bit about kind of the journey I've had in the self-driving car space. And we'll get over here, and there it works. I've been working in the space since around 2003. So of this kind of recent wave of self-driving vehicles, I've been basically in it since the beginning. Of course, the field has been around for, well, basically as long as there's been cars. And so we've just been able to kind of leverage some of the exciting work and advances around robotics and around state estimation, around sensor development. So for me, the journey began in the Atacama Desert in Chile. This was a robot called Hyperion that we had down there doing experiments with NASA, trying to figure out how would you automatically look for signs of life in the desert. And this little bicycle wheeled robot drove around at about 30 centimeters per second. And so to put that into context, if you walk with a walker, that's about the speed you go. And my PhD advisor, Red Whitaker, came down the desert to kind of meet us at our field trials and told me, hey, there's this DARPA Grand Challenge thing. We're going to build robots to drive across the desert at 50 miles per hour. And I thought that just sounded really cool. And so I jumped in, and so we set to work with a ragtag team, as one does, and we put together Sandstorm. And this is kind of the kind of, I don't know, the Lucy of modern self-driving vehicles. So if you look at it, if you look at the vehicle here, on the front, you can see an upside down paper towel dispenser. Turns out that's a millimeter wave radar. Below that, you can see a pair of things that look like coffee makers. And there's this big Eye of Sauron thing up at the top. Those are actually laser rangefinders, scanning laser rangefinders, or lidar. And then there's a little tube in front of the teddy bear there, which is a camera. So we're using that to see things in the world, of course. The big white box is the computer enclosure. And then this vehicle, actually, one of the big innovations was, this is the first time we used high definition maps to understand the terrain ahead of the vehicle to allow it to drive at speed. So the challenge was to drive from Los Angeles to Las Vegas, and to do that in a short amount of time. So we had to go quickly. It's about 150 miles. So we built Sandstorm. We took it out to the desert to go test it. We had good days, and then we had bad days. And For those of you following along, the video on the bottom right is what it looks like when you roll your several $100,000 robot. I've done this for you. You don't need to anymore. So there's the experience. Obviously, the black part's supposed to be down. The insight here, it's an expensive insight to gather, was that move fast and break things isn't really the right thing to be doing in this space. The way this came about was we were at this very flat, simple test track, and we wanted to show for the first time we could actually drive 150 miles without having to disengage the system. And so we set it going, and it did a lap, and it was working really well, and it was going at 30 miles an hour. And I, being a brilliant graduate student, said, well, if we want to do 150 miles at 30 miles per hour, that'll take 5 hours. If we crank it up to 50 miles per hour, that'll take 3 hours, and 3 is less than 5, and so that's better. And so anyway, we set it off. It did one very nice lap at 50 miles an hour, and then the next one it bit into some soft sand and rolled over, and I ended up getting beeped on the History Channel as they ran out to film the wreckage. So we put this thing back together. We took it down to Los Angeles to compete in the first DARPA Grand Challenge back in 2004. And it was really a truly incredible, inspirational day. There was a collection of robots. Our robot, despite having been put back together, qualified first, headed off into the desert, and that was it. And it was kind of like the day your first kid goes off to school. Right, you've been with this thing the whole time, and it's off, and there's other people monitoring as it drives without our support and our assistance for what we hoped would be 150 miles. Well, it turns out we went about 7.5 miles out into the desert. This is actually a picture here of the final resting place of the vehicle. And what had happened is we didn't estimate we didn't do a good job of managing errors in the system. We got a little bit to the left of the road center, and the vehicle got high centered up on this berm. The control loop kicked in. It tried really hard to get unstuck, so the poor wheels were spinning like crazy. Eventually, the folks monitoring it realized it was not going anywhere, so they told it to stop, snaps its axles, and that was the end of its day. Now, we went 7.5 out of 150 miles, so wasn't exactly what we hoped. But we did do it at high speed, and at the time, this is the kind of the productive distance and speed that we traveled was a huge step forward. What was also exciting is on the way to 7.5 miles, we drove through 3 fence posts, and we're not necessarily proud of that, but it was really good for the robot that went behind us, which was a much smaller, lighter vehicle that went right down our tracks. And if we hadn't taken those fence posts out, it would have gotten stuck sooner. So this was as far as anybody went this year. The media, of course, had a field day. Imagine again, a marathon, an Olympic marathon where the best runner goes 2 miles. You can kind of, the headlines write themselves. But the Defense Department realized this was a huge step forward. And so they said, okay, go back to where you came from, work a bit harder, come back a year later, and we'll have another competition. And this time, instead of having $1 million prize for winning, we'll have a $2 million prize. And so we said, okay, that's great. We'll go back, and we built another robot, and we tested it again. Of course, this is not the right way up. So we hadn't learned all our lessons. By the way, I haven't rolled another robot since then, so I'm proud of that, I guess. But this was Highlander. We put it back together again. It was about the same 10 days before the competition, headed out to the California desert. And this time, the field had made significant progress. And of the 150 miles, or I guess it was 125 miles this year, 5 vehicles actually completed it. Both the teams from Carnegie Mellon, obviously the Stanford team with Stanley here was the fastest that day. And then a giant, big military truck actually completed it after having to sleep out in the desert for the night. And a really plucky team from New Orleans also finished as well. And so we got up on our soapboxes and we said, look, automated driving, we didn't actually use the term self-driving vehicles back then. Robots are going to help our young men and women on the battlefield, and we're going to be able to move supplies in foreign countries and not put them at risk. And this is wonderful. And the Defense Department said, that's great, but it turns out that if you're going to drive vehicles around, they have to interact with other traffic, and they can't just drive on the road, they have to drive on their side of the road. And so they came up with the next competition, which was the DARPA Urban Challenge. And here the idea was that we were going to have to drive 60 miles around an abandoned airbase and do that obeying basic traffic rules and interacting with other vehicles on the road. And so, well, I figure I'm talking to Berkeley, so this is probably a safe video to show. This is one of my favorite robot videos of all time because I'm a Carnegie Mellon person. This is MIT and Cornell having what I believe is the first self-driving vehicle crash. And I show this video for a couple of reasons. One, it's a little fun to make fun of, it's kind of fun to make fun of MIT and Cornell. But the other is this really highlights kind of the heart of the challenge in self-driving, and that's really understanding other actors on the road. And here what's happening is the Cornell vehicle has stopped for some reason. The MIT vehicle is approached, thinks it can get past that vehicle because it perceives it to be stopped. And then surprisingly, the MIT vehicle or the Cornell vehicle starts moving and they have it coming together. And this kind of challenge is one that we continue to have today in the space of understanding the intent of other actors on the road and predicting or forecasting their near-term behavior. But at the end of the day, 6 teams actually did finish the challenge. The team that I happened to be the technical director for, we won that day, which was nice. And then Stanford, of course, did tremendously. Virginia Tech and others finished. So it was an incredible day for the field. Once again, we got up on our soapboxes and said, look, this is coming. This was, going on 15 years ago now. These vehicles are going to transform the world. And at that point, well, it got very quiet. The Defense Department had said they'd basically done their part, at least DARPA had, and that this should go off to private industry. Private industry said, well, it's a little speculative, too soon. And so a lot of the energy that built through the 4 years of competition quite rapidly dissipated. Until in 2009, 2008, I got a phone call from Google and they asked me to come out and help build the Google self-driving car program. And at first it was, this is pretty speculative, kind of Dread Pirate Roberts-esque. You can come have a job for the first 2 years, but after that, we'll probably fire you. And we set for ourselves a goal that was to drive 100,000 miles of roads, which was an order of magnitude more than anyone had done before, and to drive 1,000 miles of really interesting roads to understand the capabilities of the vehicle. And long story short, within about 18 months, we'd actually accomplished those goals, and the Google self-driving car program was off to the races. We had a lot of amazing firsts during my time at Google with that program. One of the most fun well, I don't know, most fun, but interesting ones was the time that our little self-driving car got pulled over by the police. And what's fun about this, or interesting about this, is that the car actually wasn't doing anything wrong. Fundamentally, the police officer was just curious, wanted to understand how the vehicle operated, what was going on, and pulled it over to ask some questions. And this, of course, made national media. Google self-driving car pulled over by the police. And so the learning that I got from this event was really, it's important when you're on the vanguard of a technology to communicate to all of the stakeholders, right? To help them understand what we're doing, why we're doing, what the opportunities are, and help build the community around this, and not just be kind of in your cocoon focusing on the technology. So very much lesson learned here. So I had an incredible time at Google, an amazing company, a great group of people to work with. And then ultimately in 2016, I decided it was time to move on. And I spent a few months trying to figure out what I would go and do next. And ultimately came to the conclusion that there was an incredible opportunity to build a company in this space. And founded Aurora with 2 amazing people, with Drew Bagnell, who's another Carnegie Mellon alum, one of the just incredible people in robotics and machine learning. And then Sterling Anderson, who is an MIT grad, which I don't hold against him, but went to Tesla and helped launch Model X and Autopilot. And for the last 4.5 years, we've been building Aurora. We've grown the company. We're about 1,600 people today, and we're on this mission of delivering the benefits of self-driving technology safely, quickly, and broadly. So when we talk about the benefits of that, what do we mean? Well, first, globally, traffic fatalities are a pandemic. Something like 1.3 million people die every year on the world's roads. That means in the hour that we're going to be together today, 154 people are going to lose their lives. And there's just an incredible opportunity to do something about this, because the vast majority of those fatalities, the vast majority of traffic accidents are due to people making bad decisions when driving. And not because they're bad drivers in general, but in specific, they're distracted and looking at a phone, or they're tired and unable to pay enough attention, or they're distracted and just, this bit of the commute is boring every day, so I don't need to put my full brain power on it, and something surprising happens. And so with automated vehicles, we can make it so that they're always paying attention. In moving people through the world, there's an incredible opportunity to expand access. So just in America, 25.5 million people don't have the same privilege that many of us would take for granted any given day. We just get in a car and go. We're dependent on public transportation. We're dependent on special services, or these people are dependent on public transportation, dependent on special services to get where they need to go in life. And that limits their ability to go see their grandchildren or to get to work. And so this technology can help level the playing field for those people. And then for those of us who can drive, there are times when you can really enjoy it. And then there are times where if you enjoy it, we should probably lock you up. So when it's not pandemic time, if you're commuting on the 101 and you tell me that you enjoy that, we'll get you evaluated. And so instead of people spending an hour of their life every day that they're going to and from work, hating the people around them, getting more exhausted, more frustrated on the trip home. Imagine if those people can sit back and relax and maybe finish some work up, or watch a show, or just have a nap, or engage grossly in conversation with friends. That seems like an incredible social benefit. And then, of course, with Aurora, our first product is going to be in freight and logistics. And this is really the backbone of the US economy, backbone of the global economy. And so by making that more efficient, making that less expensive, making it more reliable and safer, we can have a profound impact on the economy and on individuals specifically. And so many of you, I'm sure, have seen the immense amount of economic excitement around this space. And so let me maybe just explain for a moment why that is. So in the US alone, trucking and freight is a $700 billion market. Ride hailing in the US today is a $35 billion market that is incredibly elastic, that as you reduce the price of delivering the ability to get from one place to another, that market will grow from $35 billion to ultimately the $1 trillion personal mobility market we have in the United States today. And then, of course, e-commerce is driving local goods delivery, and that's already a $100 billion market in the US. And across all of these, the largest, a significant cost contributor is the cost of driving the vehicle. So in trucking, it's $200 to $300 billion. In ride hailing, it's about, and local goods, it's about half of those $35 and $100 billion numbers respectively. And so there's an immense economic opportunity there. Beyond the just pure economic opportunity, though, these are jobs that first we have not enough people to fill. So in trucking in the US, we have a shortage of 60,000 drivers today. And so while people are worried, and rightfully so, about job displacement and what automation will do, the first order of business will be getting the economy moving the way that it needs to by actually augmenting the human driving fleet that's out there. So we see an incredible opportunity to be additive, and it's really the only way that we can meet the demand we have for both transportation and freight. And so at Aurora, we have been building a platform, a capability, we call it the Aurora Driver, to operate vehicles on the road, both in trucking and freight and in local goods delivery and people moving. And we've been very fortunate to pick up some incredible partners. We work with PACCAR, which makes Kenworth and Peterbilt trucks. We work with Volvo Trucks, which make Volvo trucks. And then we work with Stellantis and Toyota, two of the world's leading auto manufacturers. And the driver we're building works across all of these because while it may not be totally obvious, there's an immense amount of similarity between them. Fundamentally, self-driving is really about understanding the world around the vehicle, how it's going to evolve over the next few seconds, and then how do we drive safely through that. And with trucks, of course, there's the added complexity of it being articulated. The shifting is a little more challenging, of course, and you're more susceptible to disturbances like wind load. But the heart of it is really the same. And so if we can build a system that works for one, it'll ultimately transfer to both. There's really, when you get into the self-driving problem and trying to solve it, right now, the world is kind of split into two groups, folks that are coming at this problem from low-speed driving and folks that are coming at it from high-speed driving. In the low-speed environment, the environmental complexity is higher, right? If you think about driving through San Francisco, there's a lot more actors, there's a lot more variability in the scene. They do more unusual things, whereas when we're driving on the freeway, the scene is simpler, and honestly, the freeway network in the US is much more self-similar than the road network is, say, in a city like San Francisco. That said, in freeway driving, it's not easier. It's just differently hard because when we're driving at speed, we have a substantially more kinetic energy, of course. And so if things go wrong, they go wrong much worse, which makes the problem harder, or the implications of the problem being hard, failing being more significant. And then on top of that, you have to see dramatically further. You need to be able to look several hundred meters down the road to be able to react appropriately to whether it's a stopped vehicle on the side of the road or some other anomalous situation. Nominal driving on the freeway, I think, is universally easier, but we don't really care about nominal driving unless you're building a demonstration. For building a real product, you have to solve several nines of reliability across the space. And this is one of the places where we think as Aurora, we've got a special advantage with some of the sensor technology, the lidar technology we have. I'm going to talk a little bit about that in a few minutes. So before I jump into the lidar technology, let me just talk a little bit about perception. So I think this is probably super remedial for this audience, but perception to us really means understanding from the sensor data the stuff that's going on around the vehicle on the road. So here, this is an example of one of our trucks in Texas driving down the freeway. We're using a combination of camera, laser, and radar data to model the other actors on the road. And here, the little blue thing in the center of the screen, center bottom of the screen is our truck. The blue boxes are all the other vehicles that we're tracking on our side of the freeway as we're driving along. And you can see those represented in the camera imagery at the top right. Now, there's kind of I don't know if it's fair to say it's a debate, but there's a discussion. There's at least one party on one side of this debate about, do you really need a variety of sensors, or should you just do what people do and use your eyes or use just cameras to drive through the world? And we at Aurora are firmly in the camp that you actually need a variety of sensors to solve this problem. And that's why we use a combination of lidar, radar, and camera. It's not because we are really excited about using expensive sensors. It's because fundamentally we think it's essential to solve the problem, because these different sensors have different failure modes and limitations. So for example, cameras are challenged, particularly in low lighting conditions, right? And you don't get a direct measure of the geometry of the world, which is valuable. Radar, in contrast, has substantially lower resolution than camera data does, but can allow you to see further, can penetrate certain kinds of atmospheric disturbance, and also has this magical property of giving you instantaneously the velocity of the thing that you're measuring. And so it's powerful in helping you react sooner. And then LiDAR is somewhere between the two, where we can get a lower density, a lower resolution image than we can from cameras, but much higher than radar. We can get true geometry from the scene, so that's immensely valuable. And it turns out at Aurora, with some of the stuff we're doing, we can also get instantaneous velocity on a very high resolution through the world. And so this combination of sensors really allows us to actually deal with the long tail of challenges that you have to face when you're trying to build a real product out on the road. And just as an illustrative example, so here we're driving at night. As we come up to this corner here, there's 5 or 6 pedestrians really clustered tightly there, and trying to pick them out and separate them from the background with just the camera would be really a very challenging problem. Here, the combination of some camera data plus real-time lidar data is allowing us to do that. One of the things we're proud of at Aurora is the way we've taken the best of our understanding of the world, the kind of the experience we've had at other places, and thought about how do we actually build the next generation of technology. And this comes down to the one example of this is in the way that we fuse data in our perception system. So again, here's an example of it running. We do a combination of top-down and bottom-up perception. And let me talk to you a little bit about what that means, because it exploits both, or it allows us to both have low latency updates and really do a nice job of segmenting the world. And so when we say bottom up, what that means really is we're searching through our data, we're running our detection algorithms on that to pull out and segment interesting objects in the world. So here, again, these little boxes represent the different vehicles and the instantaneous detections that we have across the modalities we're using for sensing. When we talk about top down, what we're doing here is taking the fact that we know that there's an object in the world and then just using basically the raw sensor data to provide an update in position and state on that object. And what this means is that instead of having to wait for the whole detection cycle to execute and the several tenths of a second that might take, we can use the raw data as it streams in at several or tens of milliseconds latency to update these models and have a much more rapid response, much higher quality tracking because of that. And this really illustrates how this plays out. So here's a very difficult scene. So the car is in the middle of the scene. We're driving down the road. And if you look at the top, we'll play back in a moment here, there's a woman who's going to step off the sidewalk under the back of the car here and actually load groceries into the vehicle. And this is an extremely challenging problem because the person is very close to the vehicle. And so kind of classic segmentation approaches fail here. The approach that we're taking allows us to actually segment that person. And because of that top-down updates, we can track them very precisely. And then we can understand how much space do we need to provide to this person as we drive by. And so that's kind of a drive-by of some of our perception approach. Let me turn to a moment where we think we're doing some very exciting work as well in LiDAR. And maybe just take a step back for those of you maybe not as familiar with LiDAR as others, and kind of walk through the history. So, kind of the concept of a laser came out of initially Einstein's early work in 1917. And then the first physical laser was actually built in 1960 at the Hughes Research Lab in Malibu, California. And within a year of the first laser being built, they were actually using it to measure distance. So it's pretty clear that kind of the concept for why this was valuable was exactly on the path that we're using it for. And here's a fun little fact. So Ralph Hutchinson, the first person who grew the first ruby laser crystal, actually did that great work and then moved to Bozeman, Montana. And he was really the reason why Bozeman, Montana is a hotspot for the photonics industry. And it turns out this comes full circle in that we'll show a little bit later some of the cool work we're doing on FMCW LiDAR. About 2 years ago, we acquired a company in Bozeman, Montana that had grown up because of the photonics industry there and is now kind of leading the pack in this space. So really, really kind of fun to see how history shapes the world. So 10 years after the first laser was built, they were actually flown as a laser altimeter on Apollo 15. So here, on the bottom, here's the lunar mapping camera. And with that, it's got an altimeter, and they use that to build transects of the moon. So kind of incredible that 50 years ago, LiDAR was being used for mapping. And in this case, instead of scanning the beam today with some kind of mechanism, the scanner was actually, of course, the spaceship traversing the lunar orbit. From there, we'll fast forward to the 80s and 90s, where the first kind of ground scanning laser rangefinder was built. So here, this is NavLab. With the big blue box at the front is the Aram laser that was developed in Michigan. And here's an early point cloud from the early 80s and 90s. This then evolved into those ubiquitous, for those of us who remember, SICK coffee maker shaped laser scanners that were kind of the heart of a lot of robotics for the early 2000s and late 90s. And then one of the kind of steps forward that happened was the insight that instead of trying to spin a mirror that the laser bounces off of, why don't you just put a whole bunch of lasers and spin them around? And Velodyne was one of the companies that implemented this, and that became kind of the bread and butter of automated vehicle sensing for much of the last decade. And it actually started to make its way into pop culture. So this was a cool video from Radiohead and House of Cards where they had made that transition. So how does, and then, today we have our frequency modulated continuous wave FirstLight LiDAR, and I'll talk a little bit some of the differences and advantages of that. So for those of you who aren't familiar, the way LiDAR works is the way, things like the lunar altimeter worked is you take a laser, you pulse it, you generate a super bright dot of light, it goes out into the world, bounces back, and you measure the time of flight. So how long it took between the peak going out and the peak coming back, because of course we know how fast light travels. This is, if you can build an accurate enough clock, this works really pretty well until you start to try to measure large distances. And the reason why is because this is effectively a DC coupled system, you start competing with all of the background light. So things like the sun, things like certain headlights that are radiating at that frequency. And of course, you're limited at some point by how much power you're willing to put out, certainly in road applications, because well, you don't want to be blinding other people in the world around you. And so that traditional LiDAR is what Velodyne's been doing. That's what most of the players in the space have been doing. That was also the way early radars worked. In parallel, the radar world moved into something that is called frequency modulated continuous wave approaches. And these are really approaches where instead of sending a single pulse out, you're sending out a continuous wave, and then you're interfering those waves and looking at the phase difference between them to measure the time offset and using that, or the distance. And so what's cool about this is because of the self-heterodyne property, you get a dramatic amount of application. And so this means that for the same amount of power, you can see dramatically further. It's also, because it's not DC coupled, it's AC coupled, it means that you don't worry nearly as much about background DC signals like the sun or other vehicles' headlights. And then finally, you're actually able to measure the Doppler effect, much like we do with radar guns, so that you can actually not just get the distance to objects, but also the speed at which they're moving. And so, these are those points. We get the speed, we get interference immunity because of the frequency, the AC coupling. And then ultimately, we'll talk a little bit about photonic integration and how that can reduce the complexity of these systems. And so this is what that kind of data looks like. So here's an example of an FMCW radar, LiDAR from Blackmore driving, or from Aurora now, driving through New York. What's exciting is, for those of you who've tried to do segmentation here, it's very obvious, the different actors. And so red things are moving away, blue things are moving towards, purple things are retroreflectors. And so you can very easily pick out people moving counter to the crowd, which would be an extremely difficult segmentation problem just in and of itself, track vehicles. And because you have instantaneous velocity, you can react dramatically more quickly to the objects and respond to them. And so let me show you what this translates to. So those are kind of conceptually what FMCW is. Let me show you how this works in a real application. So here, this is a video taken from one of our vehicles operating with our FirstLight LiDAR in Texas. And on the left, we're showing traditional LiDAR. So I think in this case, it's the Hesai LiDAR. On the right, it's that Hesai LiDAR that's been augmented with a FirstLight LiDAR as well, an FMCW LiDAR. The vehicle is going to be driving down the freeway. And a few hundred meters down the road, we're going to see that there's a stopped vehicle on the shoulder. And, and the little insets on the bottom of both sides here are showing that what data we're getting back from the sensor at that location where we know the stopped vehicle is. So here we drive forward. The stopped vehicle is about to come into frame. And at this point, we've got about 7 returns off the back of that truck. And so we know that it's there. We know at this moment that it's traveling at 0 speed because those dots are white. And so now we can begin tracking it, and we can actually begin reacting to it. And if we just kind of play the video forward, it takes about 7 seconds before we get close enough that the traditional LiDAR actually gets returned to that vehicle. And so 7 seconds may not sound like a huge amount, but when you're traveling at freeway speeds, that's basically 2 football fields of travel. And so this is really the difference between being able to gracefully lane change to avoid or gracefully slow down to stop behind versus panic braking and potentially colliding with the vehicle. And at its heart, this is really the difference between actually having the technology necessary to ship a real product in this space versus having a technology that works most of the time and makes a really good demonstration, but doesn't actually solve the problem. So we're super excited about this. And it's one of the things that as Aurora, we think is a huge differentiator. It's been fun to watch. So the image on the left here was the first LiDAR unit that the Blackmore team built back in 2016. It's scrappy, as you might hope. Doesn't actually fit through the door. So they had to disassemble it and reassemble it. Today, we're at the first generation of FirstLight, and so it's now kind of roughly shoebox sized. And we have it on vehicles and we're using it today. And the big next step for us is taking that system and integrating it onto a chip and using silicon photonics to dramatically improve the manufacturability and cost of these sensors going forward. So here's an opportunity for a really quick shout out to Berkeley. I think about 2 months ago, maybe a month ago, we acquired Ours Technology, which had 6 Berkeley PhDs. So we're really proud of that. These are amazing folks that worked with and CS professors or EECS professors at Berkeley, and just building incredible technology. We're super excited to have them on board and start pushing forward with us this technology. And so what does that look like? So on the left, this is an older generation, but representative of the FirstLight LiDAR. And what you're seeing here is all of the fiber optic cable that's effectively the wiring of the system. It's expensive, it's air prone to assemble, it doesn't scale very well, it's lossy, and you can't build a lot of these. Now, of course, we've iterated the design to make it substantially simpler than this, but there's still a huge gap between that and what's possible when we can take this design and embed it in a chip. And it has some, not just the kind of take the current design and make it simpler, but you can make it dramatically better. So we can have substantially more optical antennas, which improves the performance of the system. We can take, dramatic number of components and integrate them onto the circuit. It's all of the great stuff, of course, that happened in the move from discrete components and electronics to integrated circuits. And this will really, moves the manufacturing design of our system from something where it is, comparatively expensive in the moment to something that, we can basically send to a fab, fabricate at scale and produce, substantial quantities of. So really excited about the scalability, lower cost, and manufacturability of the whole thing. And so this is kind of, we're at the cusp, I think, of automated vehicles coming to market. So today you can go to suburban Phoenix and ride in a self-driving car for a short distance. Over the coming decade, that this is going to move from something that looks like a demonstration to become ubiquitous. At Aurora, we're betting that the right path forward will be in trucking because the road networks look so similar, because the opportunity is so important and profound that we expect to be able to build that and then move into passenger mobility. I think it's still very early days. We're seeing in the industry substantial consolidation already, but we expect that to continue, and we expect to. Well, I can tell you, I've been working in the space for 17 years, and every year we feel a little bit closer, and now we're very much on the cusp of this actually happening. And it's going to be an exciting time for anyone who's excited about this space to come and involve and kind of help make it so that the world roads are dramatically safer, so that people's parents don't have to give up their keys, and that entrepreneurs honestly can get their goods farther to market and have a bigger impact in the world. So that was the presentation. I'd love to take questions and talk with you all. Thank you.
Great. Yeah, thank you, Chris. That was, I appreciate the complete story of even all the way back to the beginning. I think people appreciate seeing the struggles early on, for sure. People can ask questions in chat. Let me just ask something to start us off, which was, Aurora's made a specific design decision to more augment existing vehicles, and I can see a lot of advantage to that, but there are trade-offs, and I don't know if you look big picture, is the landscape going to be more mixed, or is it going to be early adoption really favors the kind of Aurora strategy, and then maybe we do need some design decisions? You can imagine you could redesign entire vehicles if you take the latter into consideration.
Yeah, no, I think that ultimately we will be building fleets of very unique vehicles, and it'll actually lead to another golden age of design in vehicle. But it turns out that building cars is immensely capitally intense. And so right now, where we have a lot of strong perspectives on what the business models will look like and what will resonate with consumers and how this should roll out, we haven't proven it. And so it seems like the right answer is, let's take vehicles that exist. We can't just go and buy them from a dealership and bolt on. We have to actually work with the manufacturer to make the steering systems, make the brake systems, make the electrical systems more robust. But take those vehicles, make the minimal changes we can to them, deploy them, learn from that experience, and then start to specialize the vehicles as we show and prove the business case of this. So it's, for us, I think it's really just, it's the path by which you get there, as opposed to a fundamental belief that cars should look like they do today.
Great. Okay, so we have questions, both the panelists and also the, let me take one from Armin and then I'll come back to our panelists. Armin, you might be able to ask your question directly. Did you want to do that? You should be able to unmute yourself.
Hi, cool. I didn't know that was a feature of these Zoom meetings. So yeah, my question was on a lot of the 3D visualizations, those OpenGL views, it looked like the cars in the distance that were parked were surprisingly stable. So I was wondering if that was a post-processing step, or if you actually have stable tracks for cars that are that far in the distance. And I think in the Q&A, I can point you to a specific slide if you want that. No,
I can tell you that all of the data that I showed here was real-time data. I'm showing you the good stuff. I don't want to say that like it's always all that great, but we've been really thoughtful about the architecture and really proud of the results that we have.
Awesome, thank you.
Yeah.
Eli, I think you had a question.
Yes, I was very interested that you emphasized the lidar so much, but it's got to be one of many sensor systems that you're planning to use. And is that because it's just easier to talk about lidar, or some of it came from our department at Berkeley, or is it is it for some other reason? And sort of a subsidiary question is, what happened to ultrasound?
Yeah, so it's the place where I think we're doing something really unique and exciting. So as we've built the hardware kit for the Aurora Driver, we've thought hard about where is there a strategic opportunity, where is there something that we can do differentiated that you can't just kind of buy. And it turns out that, you know, trying to design our own imagers is probably a lost cause, right? There's companies out there, Sony, for example, that makes incredible imagers, and they've got a market that's going to drive the quality of those. And so we use commercial components for that, and then build our own camera modules. Similar with radar, we're certainly exploring some interesting things in radar, but modern automotive imaging radar is really impressive. And so we're able to work with partners to pull that in and use it as part of the Aurora Driver. The lidar that we're building, that's something that only Aurora has, that FMCW capability to see that range, and then ultimately to fold in the great groups of folks to transform that to an integrated photonic solution. You know, again, that's something I think we're doing uniquely.
And what about the ultrasound?
Yeah, ultrasound just doesn't have the range, right? You know, it's fantastic in water where it couples well, but in air it doesn't couple particularly well, and so you just can't get enough range to do something really useful for it. And as you're trying to drive at freeway speeds, you know, the air volume that's moving, it's just not really a useful sensor unless you're at really low speeds. And even there, you know, the failure modes, like if you're wearing something fuzzy, it's going to have a hard time reliably detecting you. So don't use your ultrasounds to avoid, say, your cat.
Great. Jihao, you had a question. I think you might be able to unmute yourself and ask.
Yeah, thanks, Chris, for a great talk. So my question is, so we also have the algorithm and the software, say machine learning and the reinforcement learning. And you talk about lots about the hardware, say the lidar and the lidar. And so what's your view on the two things? And what do you think eventually for the autonomous driving, which one will lead to the success, or the other way, how they interact with each other? Thanks.
Sorry, so the question is, I talked about lasers and LiDAR. Don't you guys use machine learning and reinforcement learning?
Yeah. So how this algorithm side can help the autonomous driving?
Yeah, I apologize for maybe not conveying that effectively. So absolutely, there's an immense amount of software in a system, you know, and we do we use reinforcement learning. We use you know, various other flavors of machine learning. We use kind of conventional Bayesian statistics and estimation. And it's actually one of the things we're proud of is that, you know, we don't believe there's only one tool you should use. We look at we look at common filters, and turns out that, you know, people have put a lot of effort into making that incredibly valuable. And so, you know, part of our tracking state estimation system, you know, is fundamentally kind of classic Bayesian estimation techniques, but then we layer around that some really exciting machine learned approaches for perception. We use reinforcement learning in the way we generate some of our motion planning work. So yes, it's super important.
Awesome, thanks.
Thank you.
Great. Okay, so I appreciate a lot of good questions are coming in. I'm going to take one more from the Q&A, and then we have a bunch of people with hand raised, which I promise we'll get to you. But Stephen, did you want to ask your question?
Yeah, hi, Chris. This is Steve Schlatover. I wanted to ask you, how do you balance the opportunities you get from machine learning with the challenges of verifying that you're going to get a correct response under all the conditions you're likely to encounter out on the road?
Yeah. No, and so the way we try to implement this, and you know, the way we're implementing this is we actually have explicitly coded constraints that we bound the response to the machine learned system to. So, for example, we learn a braking model for following another vehicle, but we hard code constraints that's limit how close we can be, assuming that the other vehicle can stop at some peak deceleration, so that the machine learning can't extrapolate across that boundary. One of the things I would point out, though, is that this is not a pure machine learning, not machine learning verification problem. That kind of pre-deep learned models that were hand coded were immensely complicated, and the idea that they were significantly more provable or verifiable than a thoughtfully trained deep learned model, I think is something that it's not quite accurate, right? That both of these were going to have dramatic challenges in verification and validation.
Great. Emmanuel, I think you had a question next. You should be able to unmute yourself if you'd like to ask. Are you still there, Emmanuel?
I see him still there, but muted.
Yeah, okay, let me, okay, we'll move on and maybe come back. We'll just pause. So, Boubacar.
Yeah, great talk. So I mean, I was just wondering if there was any regulation regarding the power that lidar can emit, and I mean, if not, how much power are you emitting, and how far away do you want to see?
Yeah, no, there absolutely is. There are standards for that, eye safety standards, and we certainly measure our system and evaluate against it. Right, they're a function both of wavelength. The standards, when you look at them, look at both naked eye and kind of telescope tests to make sure that you don't end up hurting someone who's looking at through binoculars at range. So for us, we want to see a few hundred meters out, so 300 to 400 meters out is what we're looking to be able to detect some of the classes of objects at.
Great, thanks. Ming, moving on to you.
Chris, thank you very much. A very impressive talk, and congratulations for acquiring a brilliant Berkeley team. So I have a question about the impact of weather. Under non-ideal weather conditions, does LiDAR perform better? How does that compare with a camera? Both are, visual based.
Yeah, and I think part of it is going to be a function of the wavelengths that you're using for the LiDAR. I guess when I think about this, I think that it's really not a whole lot different than people driving through the world, except that as we implement the algorithms, we're going to estimate our certainty or our confidence and control based on that. And I get this question with fog, which is, I guess, a variant on precipitation. And if you're a person, certain classes of people, and you're driving through a fog bank, you're like, look, I can't see anything in front of me. I'll drive at 65 miles an hour. And I call that faith-based driving, right? You're just hoping that there's nothing bad that's going to happen. And this is where you get these 50, 100 car pileups, is that people drive like that. And then, they don't really understand that they're out of their sensor horizon. In contrast, we'll actually understand how far we're seeing. And so, our systems will ultimately slow down and not drive beyond the sensing horizon. And I expect them to be incrementally better than people, and I think expect them to obviously have a better better understanding of their ability than many people have.
Great, thanks, Ming. Ganesh Kumar, I think you had a question on the chat, but you're welcome to ask it here now.
Sure. Thanks a lot for the talk. I've been interested in autonomous vehicles for a while, so it's fascinating to listen to it. My question is, how did Aurora decide what level of autonomy to prioritize developing? And then in the next few years, what do you think are the biggest roadblocks to safely deploy level 5 autonomous vehicles?
Yeah, so for those of you who aren't familiar, the SAE came up with 5 levels of autonomy, where level 0 is no automation. Level 1 is a single axis of automation. Level 2 is 2 axes of automation, but the driver has to be paying attention. We'll skip level 3 because I don't think it really exists. Level 4 is the vehicle's responsible for the whole driving task, but can't drive everywhere. And level 5 is vehicles responsible for the whole driving task, but can drive everywhere. And so at Aurora, we're focused on level 4 because we think that's the one that actually is useful. And so the vehicle is able to do all the driving, but it can't drive literally everywhere. And so that may mean it only operates on the US freeway network, or it only operates in San Francisco. And if you think about as a commercial product, that's what you want. I don't need something that drives the Appalachian Trail or is willing to drive on the beach in Mexico. At Aurora, we decided to go after level 4 because it seemed like the level 2 technologies that are out there, these driver assistance capabilities, they were well in hand with the tier 1 auto manufacturers, so the Bosches and Continentals and Aptives of the world. And that they were discretely different than what it was going to take to solve the level 4 self-driving system case. And that's where we saw the opportunity to have the biggest social impact, ultimately the biggest economic impact, and build something that mattered.
Thank you.
Thanks.
Great. So Emmanuel, are you there, or we're not sure? We lost you for a second. Are you there? You'd like to ask your question? I'm going to take that as no for now. I actually had another question here, which was, you hear a lot about essentially all the techniques that you're talking about, different types of sensors, different kinds of machine learning. One thing I hear less about, and maybe I'm just, it's not explicitly the domain that I'm, work in, but how important could networking be of sharing kind of knowledge about even, instantaneous road conditions, cars, velocities, just to get a larger, more global picture? It might create different kinds of reaction styles or kind of strategies for navigating. Obviously, we're used to what I would consider like course level, like traffic. I'm talking about still, I think you know what I mean.
Yeah, no, I think it's actually a really interesting opportunity. Today our approach is that'll be nice if it happens, and it's something where we don't have to scale yet to get real benefit from very high frequency updates, right? So if you imagine that 1 in 10 vehicles on the road were a self-driving vehicle and could share the sensor data, that would give you profound ability to kind of look 100 meters down the road and see what's going on and start to react and shift earlier. And so I think as we deploy the technology, as we start to get to scale, we'll think more about that. You ultimately can't be totally reliant on it, because if the network drops out, you won't have that access to that information. But it seems like a really interesting opportunity and something that isn't the first phase, but will be an optimization in the second or third phase.
Yeah, very cool. I think it's a really hot topic, and it's also really applicable to, I don't know, real world problems. And clearly it's drawing on deep knowledge in lots of different engineering and computer science fields. And there's also a lot of ethics in here. There's a lot of things that I think, there's also PR challenges. I think there's a big problem around the fact that people think of it as, it's kind of more helping you drive rather than something that's just you're handing off all control to. I mean, I think people just haven't quite grasped that we're already using tools every day that help us auto-complete and do things. There's just a lot more at risk with these vehicles. But I think that conceptually, computing should be a partner in a lot of these things in these roles of our lives. And even like you mentioned briefly that, I think how long we will drive until you have to hand the keys over. And I think you mentioned like, hey, being able to kind of have a little autonomy as you age is a really powerful, yet another enabling factor that's really exciting.
Yeah.
Looks like Ganesh is there. You're unmuted, Ganesh. Go ahead.
Thank you. And this is sort of building upon like what Professor Paulo just mentioned regarding the ethics. And also I have a question about the regulatory environment. So there's like a lot of questions around ethical decisions that vehicles might need to make, especially when they're in dangerous situations or when they might crash. And I think there was like a bunch of studies by MIT and others about what people in different countries think would be the right decision to take. But I was wondering how much of that actually plays a role in terms of designing the system. Do you actually end up changing the loss functions or the reward functions to match what people want, like the public wants? And does that, is that something that regulators look at? And then the other aspect is, I guess the other question is, how do you think about, maybe some of the rules and around maybe, like insurance, for instance, or, if that, like such rules or like could be used to build some, new business models. Maybe that part wasn't clear, but
no, I think there's interesting things to do there for sure. So on the ethics side of it, a lot of time, a lot of mental energy has been burnt on the trolley car problem, right? You're in a no-win situation, and what do you do? I think a lot of that is really fun, interesting study of society, but honestly, not really core to solving this problem, right? If you can just think through your lifetime, how often have you been in a no-win situation, and really across the fatalities that do occur on the road? This is not a very, if there's, event per 100 million miles where someone dies, I guess it's about 85 million miles. The likelihood that you're in one of these no-win scenarios is probably a couple of orders of magnitude behind that. So I don't think it's fundamental to solving the problem, but I do think that communicating what the expectation is, I think, is important. And I do think ultimately there will be a role for a societal conversation around this, but it's certainly not at the top of my worry list today. And it's not one of the things that the regulators are particularly focused on at this time. On the insurance side of this and frameworks there, that'll ultimately be an economic question. Today, because the human is responsible for the safety of the vehicle when they're driving it, we insure the human driver. And when the vehicle is responsible for the safety of driving it, that'll be the thing that ultimately needs to be insured. And things will move from something that looks like driver's insurance today to something that looks much more like product liability insurance. And exactly how that gets structured and who pays for it, that'll purely be a conversation around economics and who's taking which risks and who's getting rewarded for delivering the service. I think in the long term, there'll be immense value in the government providing some kind of boundaries here in the same way they do for air travel and around vaccination, because there'll be an immense societal benefit to this. And so the government's role in kind of spurring that forward, I think, will be important.
Excellent, thanks. And sorry I didn't see your question earlier. You had a follow-up question, Ganesh. Great, Eli, do you want to wrap us up, or do you have some follow-up?
Yeah, let me wrap it up. It's been terrific, Chris, and I hope we can meet in person, and we will take you out for a postponed celebratory dinner.
Well, thank you. That'd be lovely. And I very much, I'm sad not to see everyone in 3D today, but look forward to it. And thanks for being here.
And best of luck with Aurora and everything you're trying to accomplish.
Thank you so much. Appreciate it.
Yeah, you'll have to come visit us in a self-driven car. That's the requirement, right? There's vehicle.
I'm looking forward to that. That'll be good.
All right. Thank you, everyone. And thank you, Chris. We will see everyone soon, I hope, in some way or shape or form. But thank you for a great talk. Really, really appreciate it, Chris. Thank you.
Thank you. Take care.